Hey everyone, welcome to the channel. Today we're diving into Phi-4, a new open source AI model from Microsoft Research. In this video, we'll explore what Phi-4 is, how it's trained, what sets it apart, and how you can get started using it on your own projects. If you're curious about large language models, advanced reasoning, or just love building with the latest AI tools, stick around because this might be the model for you. Head over to Microsoft's page on Hugging Face, where you will find two types of models available for download. One is the tensor file format, which can be loaded using Python to run the model and perform inference. The other is a GGUF file format, which is compatible with tools like Ollama or LM Studio. Instead of handling this manually, we will rely on our Ollama library to simplify the process in this scenario. If you're familiar with installing and using Ollama, proceed as usual. If not, you can refer to our previous videos or visit Ollama's GitHub repository to find the README file with installation instructions for your operating system. Once ready, visit Ollama's website and search for Phi-4. Use the drop-down menu to select View All and access all the quantized variation available for your system. The 14 billion floating point 16 is the non-quantized model, but running it on my system, RTX 3090 with 24 gigabytes of VRAM, is slightly slow. Instead, the 14 billion quantized 8 model, which is smaller file size and minimal performance loss, is a better option for this tutorial. If you have a lower GPU, opt for the quantized 4 model. Let's talk about why Phi-4 is a standout, especially for its size. Phi-4 is a transformer model developed by Microsoft Research with 14 billion parameters. What makes it special is focus on quality despite being small compared to other models with over 70 billion parameters. It's built on carefully curated mix of public domain data, synthetic data, and academic Q&A dataset. The goal was to create a model capable of advanced reasoning while maintaining a smaller footprint. With a context length of up to 16,000 tokens, it was released in December 2024 under MIT license, and it's not just designed for chat, it excels in math, coding, complex reasoning, and answering questions. In short, Phi-4 is powerful and versatile, packing a lot of capabilities into a compact model. While the model itself doesn't support tools and function calling directly, it can generate structured JSON outputs. Just like in the previous tutorials, we'll use the same code to emulate function calling, making it easy to integrate the model's response into various workflows. In this video, we'll go over how to load the Phi-4 model using Python, Ollama, and .NET. Although you can load the model in .NET, the Microsoft team used tokenization that is not currently supported. I loaded the model and was able to generate a response, but the behavior did yield unexpected results. There is a discussion on GitHub, and the ML.NET team is aware of it. In order to run the Phi-4 using Python locally, you'll need a GPU that can handle it. For my system, a 3090 RTX NVIDIA GPU with 24 gigs of VRAM loads the model but is slow in inference. In this example, we'll use Python to run inference on Phi-4 and utilize our existing code for IBM's Granite model to demonstrate function calling capabilities. I have slightly modified the .NET code to use a configuration file for obtaining the OpenAI compatible API endpoint URL. Then we start a simple chat without enabling function calling features and display the results in the console. Afterward, the rest of the process remains the same. We pass the tool, our functions, and then ask a question. The Python code identifies when a function call is needed, executes it, and returns the results. Finally, the results are passed back to Phi-4 for processing and response. Now let's review the Python code. It's based on our work with IBM's Granite video, just as before, and has been modified to work with Phi-4. Since Phi-4 does not natively support function calling, most of the work is handled by the service and utility Python script files. When a request is received, we first check if it involves a tool call. This means that if a tool was called in a previous step, we now need to generate a response based on that tool call. Next, we verify if the request has passed any tools for the language model to use. If tools are provided, we extract the tool we need to call. If no tool is specified, we proceed without one. If a tool is found, we set up the response accordingly. I will include the code for you to explore and debug further. Now let's take a look at using Phi-4 using Ollama. I've downloaded both the floating point 16 version and the quantized 8 version of the Pi model. The quantized 8 version runs really well on my RTX 3090 with room to spare with VRAM. The FP16 also runs well on the VRAM but maxes out and it is offloaded using my system memory. Although it runs a bit slow, the performance is small. Let's take a closer look at the service. The service is built using ASP.NET Core Web API and supports OpenAI standard chat request and response with function calling. In this example, we're using the OpenAI.NET code where they are showcasing the function calling features. We've ported the example from their repository into our Granite example. There are two functions, one get current location, where it will return a static response of San Francisco, and another get current weather, accepting a location and returning the temperature, which is also static. When we run the program, the response of what is the weather like today is sent to the .NET service, where it will then pass the response to Ollama with the model and the response, in our case, Phi-4 quantized 8. The Phi-4 model will return the function to be called, in this case, get current location, as the user's query has not specified that, and the get current weather requires location. The client code will recognize based on the response that we need to call a function where we then pass the result back to the service without requiring user interaction. Let's take a closer look at the service. When a request is received, we first check if a tool call is required by looking for an array of tools in the request. When we find the tools, we create a tool prompt with a few short examples and send it to the Phi-4 model. We configure Phi-4 with top P of 1 and temperature of 0 to limit creativity in its response. After getting the response, we tell the caller they need to execute a function. In our case, the caller requires another tool call. We process its response, create a new prompt, and send it back to Phi-4. This prompt is different as it's a response from the original request and the subsequent tool call. Finally, we combine the tool's responses with the user's original question and send it to Phi-4 for the final response. That's all there is to it. Now you can use Phi-4 with function calling capabilities. The service is designed to only return one function, but you can modify the prompt to allow multiple functions to be called. We leave that up to you. Thanks for watching another Coding AI with C# tutorial. If you enjoyed this content, hit like and subscribe for more.